Recording. All right. So from the last time we were discussing about like linked lists in a certain way. Normally we are only used to writing out the structs for the node, and then we use it in our normal programming of linked lists, right? But then sometimes that's not very enough or very good. For example, in our case of wanting to work with stacks and queues. Okay, so while we are doing this, you are thinking of stacks and queues, right? After we are done, you are going to be able to use it to implement whatever you need to do with the stack or the queue, because this will help us to really nail the constraint that comes with a stack and a queue, right? Especially the queue, because we need to insert at one point and remove from the other. Okay, so usually we are used to seeing this kind of let's say this structure. We've been seeing something like, let's say we have something like type def to define a new type. So type def, then we have the struct. Let's say we can call it a node structure, and then inside of that we have, let's say, the int data, and then another struct, node s pointing to the next, right? So I'm using a singly linked list for this particular um, presentation, or this thing that we are doing here, right? So this is the usual method that we are used to seeing, where we declare our linked list like this. Then to work with it, we have something also like this, where we see something like we have say, since we have the type already, we can say the head is equal to null, right, as our beginning, like as our starting point. Then if you want to insert into the list, let's say we have a function where we use to add to the list. So you can say that we are going to add to the list, and then we will pass in the, oops, sorry, we pass in the address of the head, and then the data that we want to add, right? So I'll change this and then make it something like, let's say I'll call this append, right? So that it appends to the end of the list, or inserts to the list, right? So basically here we have, let's say, a function that will append data to the list, right? So if it is empty, it will do that. We understand that up to this point, right? But then normally what happens is that we don't have an actual structure of how the linked list is looking. All that we have is this pointer to the head node, right? And sometimes it's not very efficient in terms of when we want to be inserting at the end of the list, right? So here, when we insert into the list, for instance, so let's say, for instance, when we started this here, the head was empty. There was nothing there, right? So here's our head. So here's the head that we have. Currently, it was pointing to nothing, right? So our head node was null in the beginning. Then we appended something, right? So that's the first thing that we appended, or we inserted into the list. So once we do that, this head node is going to point to something. And remember, we are always keeping the address of the head node. So let's say that when we created that, we have this address here, or this node here having the address of 100. And then we give it the data 10, right? And its next is now, because we don't know that yet. And that's the only thing that we are inserting so far. So now the head node is now going to point to this node, right? Or the head pointer is going to point to this node, right? So now that we have this, we understand that this head over here is now pointing to this new node that we've created. And that's all that we have, right? So we understand that this is how the list is going to look like. This node currently points to nothing because there's nothing after it. Okay. Now, if you wanted to insert something else, we come here and then we can say append, we insert into the head one more time. And let's say here we want to insert 15, right? When we say this, we come to the head, we see that there's something there, right? So now what we have to do is to traverse all the way to the end of the list, right? And then insert the node over there, which let's say here too, we have a new node, which is like this. And then let's say this one had the address of 150, right? Just for convenience. Then its data is 15, and its next is, let's say, now in the beginning. We don't know where it's going to go yet. But then after we normally traverse to the end of the list, right, where we do the tail.next is not equal to now. And once we get to that place, we know that we are at the end, right? So once we get to the end, we know that we normally change the next pointer of the last node and then point it to the new tail node or to the new node that we've created, and then we get rid of these pointers or the previous place that it was pointing to the end, right? So here now we have this, and as the final thing, here now the next address is going to point to the 150, right? So again, if we needed to insert to the end of the list, let's say I do another append to the head, and then here, let's say I'm putting in 3, right? Now again, I'll also start from the head node, move to the move from the first to the second, and now okay, now I know that I'm on the last node, which is the like the node that has the next field as now. Then I would also append that. Okay, so now here, let's say this node over here has this, right? It has this value as 3, and then its next we don't know yet, so we say now. And let's say this one had the address of 200, right? In the same way, we have probably like traversed to the end of the list, so now we know that now this has to change to point to this, right? So now all that we do is to change this here and then point the next to this guy, right? So I mean, rather do it well. Right? So it pointing to the node. The fact that it's pointed here doesn't mean it's pointing to the next field of the new node, right? I'm just trying to do that here. So now that we know that it is pointing to the next node, which has the address of 200, the address field is going to change, right? Not normally we don't see that, but here is used for the ease of our references. So now we see that the next pointer of this new node is going to be now because that's the last node, right? So you see that here is not being drawn contiguously, and it's also intentional because like linked lists are not like that linear way that we normally see them. They are cutting across the memory, right? So this is like the normal way that we are used to seeing this work, right? Every time we need to insert to the end of the list, we have to start from the beginning and then we go all the way to the end, then insert the node, right? This is just a linked list of 3 nodes. But if it was a linked list of about 100 nodes, if we need to insert the 101st node, we will have to, did I say 101? I mean, 100 and, I think that's the right way to say it, right? Yeah, or the like the next position. Sometimes words can really play with you. So when we need to insert into the lists after the 100th node, we would have to go all the way from 1 all the way to 100 before we will be able to insert that node. And that's not very efficient, right? So what I'm proposing here is that we would rather do something much better, right? Where we not only have the address of the head node in this way, but we're also going to keep the address of the tail node. So this time around, we are not going to really do this method as in just within the place that we are using the linked list, we just declare the head. We're actually also going to create a structure for the linked list itself. So this is for the node structure. Here we're going to have another one for the linked list structure, right? So here is what we are going to do. right? So here I'll have another thing here, right? So I'll put that inside of this here just so that maybe it's easier to um, see, right? So now the next thing that we are going to do is also going to keep track of that. But here's the advantage of what I'm trying to say. You see, if we were having the head node, right? If we're having the head node and we also had the tail node, right? So here, if I also had the tail node here, right? So in the beginning, when the the first node was inserted, right? These two are all going to point to this one for the first time because that's all that there is in the linked list, right? That's all that there is. But then, since we now know that the tail node was this in the beginning when we first inserted the node, right? When we need to do the next append, which was 15, we wouldn't have to reference the head node because we are inserting at the end of the list, not at the beginning. So now that we know that the tail node is this guy, all that we needed to do, or we would have needed to do, would have been just to move whatever it is. Because currently, remember that at that point in time, the tail node is also pointing to this, all right? And since we know that the tail node is pointing to this address, so we know the address of the tail node, okay? So now all that we would have done would have been to just come to this side, which is this guy over here, right? Currently, it is pointing to this. Then what would have just done would have been to take whatever it is. We'll take the next pointer of the tail node and pointing to the it's pointing to the what have I done? Okay, yeah. So then all that we do we would have used that to point it to the new node, right? Then after we are done, we would update this tail pointer here, right? So we'll just update the tail pointer to now say that okay, now the tail pointer is pointing to this guy, right? So the next time we need to append to the list again, we reference the tail pointer, get to its next, insert over there, then set the new tail to the new node, right? So we'll see how this is going as we talk more about it, right? So I'll get rid of all of these and then probably rather like start it from fresh so that we can really get that part. Then after that, we would see how we can write code for that if there's still time, right? So here's what I'm trying to say, right? If you were keeping the address for the head and then the tail like this, right? So here I have head and then also the tail. That's okay, fine, no problem. Let me also make this a little bigger. Okay. So now I have these two guys here, right? So now in the beginning, when I have to insert nodes, right? So here, um, both of these guys are now, right? They are not pointing to anything. Like they are now. There's nothing there, right? There's nothing there for them to work with. Then we came all the way and then appended, like the first append. We are inserting to the head node, right? Then all that we are going to do is we are going to create that node like this, for instance, and then we are going to populate it with the data. Here we said the data we are going to insert is 10. And then here, let's say the next node is now because we don't know yet, or it's pointing to nothing. There's nothing else to point to. And then here the address is also 100 for convenience, right? So in the beginning, the head and then the tail are all now. They are pointing to nothing. And we know that in the beginning, when the head is now, we just set the head to the new node. And that's going to be the same thing that we are going to do. So essentially, all that we are going to do is say that, okay, now that the head is now and the tail is now, right? Both of these guys are going to point to this new node, right? The head and then the tail are always going to point to this new node because that is the newest thing that has come, right? So new node has the head and then the tail pointing to it, right? So that will look something like what we are probably used to at this point, where we can say like the head is equal to new node, right? And then here as well, as an extra step, we say the tail is also equal to new node, right? That's something that we are coming to add up, right? So now the tail is pointing to the new node, which is the only node that we have. And then let's also show that it's pointing to nothing, right? Now, we also have another append statement. And appending, we are appending to the end of the list, or we are adding to the end of the list, which is the tail, right? But like we saw previously, in our normal implementation of the linked list, what we do is we will traverse to the end of the list before we insert at the end. But that's not very efficient. So what we have to do now is, let's say we create our new node, which is going to have the data part being 15, and then the address part being any address that we would choose for convenience. Let's say this one is going to be 150 to be consistent. Then the next address is going to be now, right? So this is the new node, right? So instead of starting from the head node and then going to the end, we already know that the tail and then the head are pointing to this guy. And for this one, it's very easy to actually spot. But you see, the thing I'm trying to say is that if you didn't have the tail node, you would have traversed first of all. But then since we know the head, sorry, the head and then the tail, we can rather reference the tail node, right? So if we reference the tail node, we can say that, okay, now the tail is like the when we reference the tail node, remember that we are still referencing this node, right? So we can now say that the tails next is equal to the new node. And that's similar to what you always do. After you traverse to the end of the list, you always say that the tail next is equal to the new node, or whatever variable that you use in that sense. You say that its next is equal to the new node. And you set the next node of the new node to now. And that's something that you've been doing all this while, right? So if something that I'm saying is not very clear, you can prompt me. But I'm under the assumption that we understand it up to this part. All right. So now we don't need to traverse again, right? So we just going to reference the tail node, which is pointing to this. All right. So now that we know that the tail node is this, what we will do is we will take the next like the next field of the tail node and then point it to the new node like that, right? Then what is going to happen is that this node over here, we already know that it has to point to now, nothing, right? Then this tail is now going to point to this new node, right? So this is going to be the extra step that is going to come inside of what we're about to do. After we change the next, we are going to also set the tail to the new node that we have, just so that we can keep track of it. It's just like how we are inserting at the head node when there's already something over there, right? So that's the thing I'm trying to bring up over here. So now that we have these, what we're going to do is we're going to remove these over here because we don't need them. And now the address part is going to be 150, right? So now we've used the tail pointer to move or to add a new node to the list. So let's do for the last one, then we'll discuss a bit more of what is really going over here. So for the third append that we are doing, we are creating another list, and then the data portion is 3. Let's make this white. It's also white. This white too. All right. So its next field is also now because we don't know yet, right? And again, we don't have to start from the head. We know the tail, right? So we reference the tail pointer, and the tail pointer is this, or the tail is pointing to this node. So we just say that, okay, the next field of the tail node is going to point to this. And that is exactly what we are going to do. We're going to say the tail node, or let's use this one, right? So the tail pointer, current tail pointer, remember, is this. It's pointing to this node. Then we are saying that this is going to now point to this new node, and the same thing is going to come again. Then the tail pointer is going to point to this new node. Also, we have to ensure that we are always setting the new nodes next to now, because that is how we are able to figure out what really is the end of the list, right? So you see what is really happening. We are not going from the head all the way to the end. We are going from the tail, and we are doing this in like straight up steps. I have to remove this one too, right? So you can see that now the tail is also moving as we are appending to the end of it, right? So we are not inserting to the, or we are not traversing the list to go all the way to the end before we insert. We have a tail pointer which allows us to insert to the list just in constant time, right? The normal method that we normally use, which is something like this, we may write the code like something like this. While let's say we may probably do something like, let's say node t temp is equal to the head, and we probably do something like while temp next is not equal to now, then we will say a temp equal to temp next, right? Then after we are done with once this loop or this condition becomes false and the loop terminates, then we will say that the temp next equal to this new node, right? This is something that we are always used to, that we traverse to the end of the list before we insert. But this is not very efficient, as I'm saying, right? So this new method that I'm talking about, what is going to happen is that right when we have to append or to insert to the end of the list, all that we are doing is this. We already know the tail node. So basically, we can really just say that, okay, well, the tail node next equal to the new node, right? And now the tail is equal to the new node, right? You see that here we are going to get shorter code and also much more efficiency. We didn't traverse, right? So here, what we are doing is we are doing something called we are doing this in terms of complexity. When I talk about it in time complexity, we are doing it in O of n, meaning that the insertion is based on the size of the list, meaning that if there's 10 nodes in the list, we have to go all the way from 1 to the 10th node before we can add the 11th node, right? But this over here, what we are doing is we are doing it in constant time, which is expressed as O of 1, meaning that we don't care about the size of the list, or our insertion is not based on the size of the list or the size of the input. It is occurring regardless of the size of the input. So whether it is 1,000 nodes, whatever we are doing is in one process, right? So that is going to be much efficient as your solution starts to grow, and the need for it to be used is going to be um, escalate, or like let's say to be more and more used by a lot of people, right? So for now, I would like to let's say ask if there's any questions so far about what we've talked about up to this point, right? Currently, we've talked about the normal method where we are using the append to insert into the list by using only the head pointer. And I also mentioned that if we have the the tail node and there's nothing inside of the list, the head and then the tail are going to point to the new node, right? So let's say this here is when the list is empty. So when the list is empty, this something is like this that is going to happen, right? So let me put this inside of something like that, right? So probably I would have to put these guys also into a few stuff, right? So let's see. Any questions so far on what we've discussed up to this point?
No question. No question. Fine. So the second method could be seen as the queue, right?
Come again?
If I the second method can be seen as the queue that you can add from both the rear and the front of the list.
Yeah. So if you need to insert at the head, you are going to reference the head pointer. If you need to insert at the end, you're going to like reference the tail pointer, right?
Okay, that's fine.
Yeah. Um, I don't know if your name is how I'm going to say it, but Matumbai, uh, Matumbai. I've not heard from you during the like since the session started. Are you with us? If you could say something. Uh, hmm, okay. Um, how about you, senior engineers? Is everything going well?
First one, everything fine. Everything nice.
Right.
I'm just looking forward to how we apply this, like how we implement this whole thing in code. So since you said you would let us go through if the time permits, I'm actually looking forward to that one too. So
All right. Okay. So let's go through to how we would go about implementing the structure for this particular one that I'm talking about. So here, there's a normal structure that we normally do, right? Like this here, we have the node structure here, right? So for the linked list structure, right? So the linked list, right? Right. Here, what we have is also something similar. Also, we would have the normal type def struct. Let's say there's going to be a list S, talking about it in terms of the list structure. And then here, what is going to happen is we are going to say that we have a node T. Remember, that is basically going to be a node. So we are going to have the head, and then also we are also going to have the tail, right? We can keep multiple information over here as well. We can have the size, the like multiple things. Okay, so as part of making it better, because sometimes we may need to find the length of the list, and every time if you need to keep traversing the list to find the size of the list, is not very good. So here I'll put a size T to keep the size of the list, right, or the length, and however you like to call it, right? So, or if you rather like to call it this way, let's say node, like I think size is much better of the word. So the size of the list, we can also keep it in this method. There are other things that you could keep. If you keep a function pointer that is run um, in multiple ways, right? There's like normally what I like to do is also have a function pointer, which is going to have a user-defined function or a system-based function that will be used to clean up the nodes when they need to be removed. Okay, but for now we'll keep it simple. Right? So here we are only keeping the head node, the tail node, and then the size. Right. The reason why we are keeping the size is for convenience, in the sense that when we need to get the size, we are going to only get it in the terms of O of 1, meaning that it's going to be a constant operation. We are going to achieve that by doing this. So every time we insert into the list, we are going to do a +1, right? and then a +1 of the list, sorry, of the size, and another +1. Sorry, +1 here, right? So every time we insert something into the list, we are incrementing the size. And conversely, if we remove from the list, we are going to decrement, right? So this is what we are looking at doing at this point, right? So this is like our whole thing that we are trying to do at this point. Like we are going to access the pointers in this fashion, right? So this is what we are going to use. And I think I missed this out here. We are going to call it list T to say that that's the list type. Okay, so now what we are going to do, or what we are really left with, is the actual implementation of everything that is going to happen, right? So here now the node structure is going to modify a few things. So let's say that if I have this node structure now, let's say here is going to be something like this that's going to happen. So instead of like calling the list in this method, I'd rather do something like this. I could say that list T, be white, list T, and then I could say that this is my list, for instance, right? Something like that. Okay, and then we can have a function that would initialize the list for us in multiple ways that we would want, and other methods, right? So when we say like list T equal to sorry, my list, let's say we can say init like this. This will initialize the head and then the tail, and also set up the size to 0 for our use case, right? So like the init method, or the init function, let's talk C. Right? So the init function will create the or will set up the required fields for the linked list. Right. So that is like what is going to happen in this case, right? Okay. So now this is like everything we need for this particular implementation. What is going to happen is we're going to see this also come up in the code. And as we go forward, we are going to be using a few other stuff if we get the time to do that. Okay. So now I have already opened up VS Code over here. So, and I've also created the directory. So if you like to follow along, you can also create a directory, and then we can work with that. Okay. So now what I'll do is I'll create a new file, and in VS Code, I can type code and then the name of the file that I would like to create. So here I'm going to create, I'll call it lists, right? So I'll create my header file, because we know that in C we would have to do that. So I'll create the header file, and then first of all, what I'll have to do is to ensure that I don't have this to basically to guard it, right? So if it is not defined, and then what I'm looking for is that list.h is not defined, then I'll go ahead and define list.h, and then also let's close it up, just so that we don't forget. But sometimes it happens, right? So let's close that up, and then say what we're actually closing. Yeah. So now, just as we saw, we would create the node structure, which is struct node s, and we have this int data, and then struct struct node s next, right? So this is usually not very new to us. We've seen this before. All right, so here, that's what we have here. Then now we are going to create the linked list structure that we just saw. So type def struct. And my system is very clever as well. So yes, so now here we're going to also have the node T, and then the head, then node T, the tail, sorry, tail. Then, as I said, you also keep track of the size of the list. And then we are going to also give with the name of that. And because I'm using size T, I would have to include the stdio library so that I can use that. And since you're also going to be using malloc, I'll bring in the std library, right? And I think that will do it for this. So this here is our struct node s, and it's the blueprint for the node, and it's basically taking the data, which is the data portion. In yours, you can write better documentation, but pointer to the next node, right? And then here, what I have is also a struct called lists s, right? And it's a blueprint for a singly linked list. Sorry, for a linked list. And here I'm having this pointer to the head node, and then tail, the pointer to the tail node. And the size, which is going to be the size or length of the linked list. Right. Quick one. Am I still audible, or is my voice going down? I realize my mic keeps reducing, like over here.
You're audible.
Am I? All right.
Yeah, you're
Okay. 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 So here I'll call it for a singly linked list. Okay. So now we have something like this, right? There's going to be what we are going to use. Okay. And for convenience sake, right, what I also like to do sometimes is to have a few things like some macros that are going to be used to return some few things, right? So we can have something like a macro, which is going to show us the the top or the first elements, or like the first, like the data at the head node, and then the data at the tail node, right? So here we can define a macro, right? So the macro, we can see something like, let's call this top, right? So this top here is going to take the lists as the input, right? Basically, like it is going to take a linked list structure as the input, and then what is going to return is going to return the lists head data, right? So it is going to return the data at the head node, which we are going to see shortly, right? And also we are also going to define one that is going to be, let's say, top. Okay, I rather call it first so that I can call this last. It also takes the same thing, and then the behavior is something similar, but this is going to take it from the tail, right? So you can see how, but just by doing this, we are able to sort of do some interesting things, right? So these two macros over here are just going to give us the first item of the list, and this is also going to give us the last item of the list, right? So now let's go ahead and then let's create our function prototype, right? So function prototypes. Come on, all right. So like we said, there's going to be a need for an init function, which will take care of initializing everything that we need to work with, right? So here, what we need to do is we'll create that function, which is called the init. It will take no arguments, and then it's going to return LST argument or LST type, right? Because we are going to initialize a list for our use. And actually here is the function prototype, not the definition. So here is what we have. And then also we are also going to do the insertion. So for the insertions, we don't really need to return anything. So I can say, I can just call it append for our use case, for instance, right? That's because that's what we were using. And it's also going to take a list, which is going to be this, right? And for other use cases too, let's say you do a pop, which is also taking a LST lists, right? So my bad here, I should also say that the data, right? We are inserting into a list and then we are going to get the data as well. Okay, so that's what is going to be used for what we need now, right? We could write other functions, and importantly, we should also write a function that prints the list. Very important, because we will need to see what we are doing so far, right? So I think this should do. Or if you have, is there something that I'm missing? In terms of the minimal functions that we can have, like the most important functions that we can have for a linked list. We are appending, we are popping, and we are also trying to print out the how do you call it? The list, right? Is there anything else that you think we can add?
Sir, we didn't get it. I didn't get it.
I was asking if there's anything else you think we can add to the functions. As in, is there any other function that you think we can write for a linked list? Right. Currently, I have a function that would initialize a list, which is not really part of a linked list operation, but then it's for the case that we need to use, like the method I'm bringing up that we are trying to learn, right? But I'm asking if like the append and then the pop method, sorry, the append and then the pop methods are enough for our use case at this point.
I was thinking about append
again?
just like the push. No, I was thinking about but the append box and yeah, for the push.
Yeah. So like this one, I'm just keeping it simple. Yeah, Eugenius.
Hello?
Eugenius.
Yeah. Please, just wanted some confirmation. Which means if let's say we are using the print list, it means it's printing everything. So if you want to print at a specific point, for that one, we'll have to write it through like the zero brackets, and we have to use that method.
Yeah, I mean, if we are printing the list, we have to start from the beginning. Right.
Okay.
Yeah.
Can we do, I don't know, print at, and then let's say the number?
Like print at a number, as in a print from a specific index or something.
Yeah, as in the ends.
So something
like the ends item in the list.
Okay, let me get it right. Like I think that, let's say we are going to print the nth element, or
Yes,
we are
yes.
going to print from the nth element.
No, the nth element.
Okay, so let's say we call this, let's say, print element at, so lists T and then lists, then the element we are trying to print also going to be an integer, right? But then know that these operations are going to be O of n most of the time, right? So the thing here is that
Yeah, but
when, yeah, but
I don't know.
the come again.
Let me quickly come in. So it means the print element at will be O of n, and then the other ones will be O of 1. If I'm not
No,
wrong.
nah. This is going to be O of n because we are going to print everything from the
From
beginning of
beginning
the
to
list.
end. Okay.
Yes. And then also here, we are also going to set within the list. And then the worst case can be that we would have to go to the end of the list, right?
Yes.
So here we are talking in terms of the worst case, right? But there are times that the data will be at the beginning or at the end, which we can use. Yes. So for our use case, we can have it at the head and we can get it, if it's at the tail, we can get it at the tail. But remember that we're also keeping the sides. So there are some very good things we can do as we go along. So we will see
Exactly.
them.
Some ideas were popping in my head, but maybe when we are done with the code, then we could.
Yeah.
I don't know. Concerning
Yeah,
the print element, but maybe when we are done writing the code.
yeah, no problem. We may not be able to finish up today, but probably we can continue tomorrow. We can continue up with the code tomorrow, right? But that's what's going to happen. But we will see what will happen. I
All
see
right.
your name is local host. Yeah, boss.
I'm
I
sure
see
it's
your
good.
hand. Okay.
Good evening.
Good evening, boss.
Good evening.
Sorry, I just have one specific question. So for this project, are we meant to use external variables? Are we allowed to?
From which cohort are you speaking from?
Cohort 1 blended.
Okay, yeah. Like the project says you can use an external variable and just one, right? Just one.
Okay, we can use just one external variable.
Yeah, that's what they allow.
Oh, sorry. This meeting is not for one blended.
No. It's a collaborated something. So it's not really based on whatever cohort you are. It's just a discussion on matters, right? So
Oh,
it's regardless of the this one that you are in, right? It happens that we are talking about linked lists, and my cohort is also doing something with time complexity, and your cohort is doing something with linked lists, working with stacks and other stuff. So it's around the same area, right? So since you guys are also working with this, I thought it's better that you understand how to work with these head and then the tail, because it will shape how you do your project and how you work with linked lists in the future as well. Right. So that's why we are doing this.
all right. Thank you. So you said I can use just one external variable.
Yeah, that's what they said.
All right. Thanks.
So okay, so for the sake of time, let's quickly try to work with the init method. Then from tomorrow we can write up the append and then the pop and the print list and those things. The code for this, I'll put it on my GitHub repo. The name of the repo is called Code Snippets, I think. So maybe you can check it up and fork it and maybe write up the code by yourself, see how you can work with that, or you can wait till tomorrow where we will talk about it. So here I'll create a file which I'll call stack ops. Normally that's how I like to call them, right? Like as in stack operations. And then I would include the lists.h file. And then I'll create my void function. Which is going to be this. What is this? Lists.h. to void, sorry, there's going to be less t in it. Then it will receive nothing. Right. So what is going to happen is we are going to do a new node structure, right? We are going to create, sorry, not a new node, a list, right? So we're going to maybe call it a list, and it's called to malloc, but we have to allocate memory for it. Okay, so malloc the size of list t, right? And we check if lists equal to now, which we understand that it means something bad happened. So we'll print out an error to the standard error to let them know that there was an error. Then we say error malloc fail. Right. And then we are going to exit with exit failure because something went wrong. Else, what is going to happen is we are going to set the list head now, just like how you would work with like the beginning of the list as we saw over here, where we start by saying the node t head is equal to now, right? But this time around, we are setting it up inside of a structure so that we can use it later. Then the list size equal to 0, right? Then we are going to return the list. Okay. So this is our first function for what we are trying to do. We are also going to write functions to append and functions to pop, and we will see how we are going to do all of that without ever needing to traverse. The only traversals we'll be doing are for the functions that we can't do away with traversals, right? So now, when someone would like to use our lists, they will first of all call this, right? So we can add some documentation to this. Here in it, say it initializes simply linked, or let's just say it initializes a linked list. It's like I can't spell. Initializes. Okay, initializes a linked list. Yeah, let's leave it like that, and then it receives nothing. Right. So example, and this is how we are going to, let's say, ask them to use this. Let's say we can say that they can say my list is equal to init and then that, right? So this is how we can ask the users to use our function, right? Let me do the right thing before Betty starts crying. Let's check this before anything else. Okay. My bad. Just like init. Okay. Yeah. I mean, it's been a while we work with Betty, so return the newly created the newly, or let's just say the initialized list. All right. I should check this again. It keeps giving me that to format the code with. Huh. All right. No problem. I would check the code and then, okay, yeah, it's neatly formatted at this point. Yeah, there was a sort of an issue with that. Let me configure this correctly. Okay, so now our first method is created, and you can use it to create new linked lists, right? I don't know why my mic keeps going down anyway. So now we have these two files created, and that's how we are going to add everything that we are going to be using. Right. So quickly, let's go ahead and then write out the prints, and like we'll write out the print list function, which is going to be simple. Like I want us to really take time and go through this one very well, so that we don't rush through it. So we would save this particular one, the append and then the pop, and I think the print element acts for tomorrow's session. Right. So let's just write the function for the print list, which is going to be a very simple one. So here I'll say print list, and then we'll just say something like that. Just set a temporary node to point to the list head, right? And we would just say that while temp is not equal to now, this is a classic something that we are used to doing. We just say print I forgot what to do. Right. So we are going to print the the list, right? But here's another nice thing that we can do. Since we are keeping the size of the list, right? We can do something like for like we can use like different methods to do this same thing, right? So we can say something like, let's say for okay, let's do this for let's say node t equal to temp, right? And then here we can say for okay, you know what, let's keep this one for tomorrow. But what we do is we would keep it's like the way that we are normally used to. Then tomorrow we would probably go through and then work with the like the other ones as well, right? So here I'll just do the usual way just to keep it simple for now. So while temp is not equal to now, we're going to print printf, print data at this point. So we're just going to print the temp data, right? And then we say temp is equal to temp, right? But then we also have to account for the cases where the list is empty. So normally I wouldn't advise that you set the list over there like that. We probably do, let's say, if the list itself equal to now, or the list head is equal to now. You just say that you can just say empty lists, or you can probably not write anything, right? Oh, sorry. Then you just return, right? Now that you are sure that there's nothing, or like there's really something in the list, now you can set it to the head, right? So something like this. Okay. So this, let's say, how we are going to use our print list function. But tomorrow we are also going to look at how we are going to write the append function and how we are going to come up with it so that we don't really have to use the traversals, and how we are going to achieve that O of 1 time complexity. Okay, so that'll be everything for today actually, and we would work on the other ones as well. But at the end of everything, we are going to work up our way to ensure that we can insert into the linked list using the tail pointer if we need to insert at the tail node, or sorry, at the end of the list. And this is going to be important when you are working with queues, because you insert at the head and you remove at you insert at the end, which is the tail, and then you remove from the head, right? So this is going to make it much more better and simpler, and we are going to see how it's really going to be beneficial as we go ahead. Okay, so let's hold on for now. Tomorrow, God willing, when we meet again, we are going to discuss how to put some of these concepts into real code. Okay, so for now, if there's any question, we can take that. And the code, like I said, is going to be in a GitHub repo that I think is called code snippet. Yeah, like that. So once I'm done, I'll push up the code to this area, and then you can access it. The link to that is here. I'll put it in the chat, just so that maybe if you like to get it right here. Okay. But I would put that inside of the of that. So I'll do the documentation and push it, right? But if there's any question, you can continue from there. So any question from today's session?
I don't have a question really, but it was a great session, and I would just like to appreciate.
Thank you. Is everyone okay? I think there's something more.
Yeah, it was fun. The session was actually didn't join it. It was a great session. Yeah. So I think that'll be it. Yeah. For questions, I don't have questions now. I actually have issues with almost a circle, but I think after here I'll contact you and then see if you can get some time for me.
Okay, cool. Okay. Matumbai, if I'm saying your name correctly so far, I've not heard from you since you joined. If you are here with us, please say a word, or probably not. So we would call it an evening then. And okay, I think I see why. So once I'm done,
Okay,
I will.
goodbye.
Sure. Once I'm done, repo that I just shared in the chat, and you can probably have access to that. So commit, the header file. Okay, so that'll be everything for today then. Thank you for joining.